Fitzmaurice, and this talk is on data-intensive applications and PHP. The term data-intensive applications comes from this book by Martin Kleppmann, and this talk is going to be part book review and part implementation guide of a project I built after reading the book. So Martin Kleppmann is a researcher at Cambridge University on database systems and database technology. He's previously worked at LinkedIn, where he was the author of their Voldemort and Kafka databases. Kafka is now Apache Kafka, and it features heavily throughout the book, unsurprisingly, given that it's his technology. PHP Southwest, people may have seen him at All Your Base Conf in 2015, where he did a talk on his bottled water change data capture system, which is a clever way of extracting data out of PostgreSQL, and I'll come on to some of those ideas later on in the talk. It's split into three parts broadly. Part one, he talks about what a database is, what kinds of databases exist, how do they work, what data structures they use under the hood. In part two, which I won't cover in this talk because it's too complicated, he talks about distributed data, so connecting multiple databases together over a network and ensuring that everything is saved and works properly. It's a very complicated topic. It's interesting and it's handled very well in the book, but there's just too much to get into with the time we've got. And in part three, he talks about batch data, streaming data, and what he thinks the future of databases and data systems is. And I'll define some of those terms later on as well. I came across this book because we had a system that we needed to rebuild. And I thought that perhaps Apache Kafka would be the right sort of tool to do it. I did some research online, found some comments from people saying that Kafka can be difficult to run. It has a lot of operational overhead. It's complicated to understand. It's a powerful tool, but it isn't suitable for all purposes. And lots of those same people said you should read the Designing Data-Intensive Applications book by the author of Kafka to understand what it's trying to do and if you think it's actually what you need. And so when I sat down to read it, I wanted to find out what a data-intensive application is. Do we actually have one? And if we do have one, what tools should we be using to handle it? And probably as importantly, if we don't have one, what tools should we be staying away from? There's no point taking in unnecessary overhead or operational expenditure trying to throw complicated solutions at what actually may be a simple problem under the hood. So when he talks about data intensive, he never actually gives a single dictionary style definition for it, but it's defined as being not compute intensive. That meaning the quantity of data you're storing, how complicated and related to that data is, and how fast it changes being more important to your application and your developers than CPU horsepower or graphics card availability. And I think all web applications are going to fall under this banner, and probably all applications on computers in general, given that a computer is a data processing device. You can't write any software without handling data in some way, shape or form. But I think it means an application as opposed to a game or something where hardware advances are going to be and making the best use of hardware is going to be more important than architectural or storage decisions, which would imply it's data intensive. So he talks about some properties of good data systems. They have to be reliable, they have to be scalable, and they have to be maintainable. So reliable means continuing to work in the presence of faults. A fault is not a failure. A failure is when the entire system stops working. A fault is something that happens quite regularly. It could be a network slowdown, a network disconnect, some disk performance issues, a configuration issue with one or two of the machines. It doesn't necessarily mean things are going to go wrong. If your software is reliable, it can continue working even when there are faults, and it stops faults from becoming failures. Scalable is being able to grow. And this isn't about simple statements like MySQL doesn't scale or MongoDB is web scale. Martin Kleppmann says those aren't useful statements because they don't really tell you how you are going to be able to change your software when growth happens. Scalability is about what are our options for coping with growth and how do we add more resources when the time comes that we need to grow. Maintainability he defines as three separate terms: operability, simplicity, and evolvability. So operability is how easy the software is to administer, how much work your sysadmin or DevOps team are going to have to do to install it, back it up, produce extra copies of the database, things like that. Simplicity is about being able to explain it. Could you sit down with another engineer from your organization and explain how the database works in a reasonable amount of time? And after hearing that explanation, could that person then go away and make meaningful changes to the database or the software that interacts with it? And evolvability is about changing over time. Data requirements are rarely static within an organization. You're going to be wanting to do new things, store extra things, access it in different ways, and a good database lets you change the way the data is stored easily. As an example, he uses Twitter. In 2016, Twitter claimed they could handle 5,000 writes a second and 300,000 reads. Those are big numbers, but they're not huge numbers for an organization with Twitter's kind of resources. And so one way of designing Twitter's architecture could be every time someone writes a tweet, it's written to the end of the tweets table. And then if you come to view your timeline, you look up all the users you're following, find the newest ones from the big table, and put it on the page. That makes writes very cheap. You're just appending to a single table, but reads become very expensive. Lots of random reads into a large table. An alternate design is to effectively have one timeline table per user. And when you write a tweet, you look up all the users who are following you and insert that into their personal timeline tables. So let's flip the problem round. Reads are now extremely cheap. You just load the pre-computed timeline from that table and display it. But writes have become variably expensive. For most of us, people like you or me, this would work fine. Turning one tweet into a couple of hundred writes is fine for Twitter. But for the larger users with millions and millions of followers, you can't turn one tweet to 30 million writes. It just doesn't scale. So they use a hybrid approach. For most of us, we have our personal timeline table and the tweets are appended to it. But for large users, they're kept in the main tweet storage table. And when we come to look at our timelines, we load the pre-computed table, look up any of those larger users, and then merge their tweets into it. So this is just one of the examples of how it doesn't actually matter what the underlying database technology is, but choosing an architectural decision helps you be reliable and scalable and maintainable. And if any of you remember Twitter from the old days when they used to use just that first single large table, they were most famous for the fail whale, the logo they put on their 500 error page. He then talks about the different kinds of database that are available. So the most common one that we'll probably all be familiar with is relational databases. Designed about in the 1970s and have been pretty dominant since then. They're composed of columns, which are stored in rows, which are stored in tables, which are stored in schemas. And the columns are fixed in a particular table. You can't alter them per row, and that is one of the main differences between relational databases and other kinds. The relational bit comes from being able to say that this particular column in one table refers to this particular row in another table, and that's powered by an index. What relational databases are really good at is normalization. So that's storing one piece of data once in one place, and then just referring to it elsewhere. It cuts down on duplication, which can help with just the quantity of data you're storing, but also helps reduce errors. You can't accidentally typo something elsewhere. And if you need to edit that piece of information, you change it in one place, and it's referenced everywhere else. I think they're so prevalent because relational databases are very easy to understand and very flexible. And I think anyone working in an office job probably would understand a relational database if they've used Excel. Excel has rows, it has columns, it has sheets, which you could refer to as tables, and you can use lookup functions to link those sheets together. So the concepts of relational databases are found throughout software that many people will use for their jobs, even if they don't consider that they actually work with a database. An alternate kind is the graph or giraffe database, as AWS analyst Corey Quinn calls them. They have two storage types, vertexes and edges. And so they look like a mind map if you've ever seen one of those. The vertex is a node, and it can have a label that says just what kind of thing it is. And then edges link two vertexes together. They have a direction, so they come from one vertex and go to another. And then edges and vertexes can both have an array of key value properties attached to them. What they're really good at is relations. Like relational databases do relations, but graph databases do it better. They handle many-to-many relationships very, very well. So if you've designed a database for a relational system that has many-to-many, you need a link table, which just has effectively primary keys from one table, primary keys from another. And reading it is pointless. That doesn't tell you anything. It's just there to work around the complexity of managing many-to-many inside a relational system. That doesn't happen for graphs. You can have your vertexes link out to as many other vertexes of any kind that you like. And what this allows is very high performance traversal and graph algorithms. So at X24 we use Neo4j, which is probably the most common graph database around at the moment. We took our main entities from MySQL and we stored them in the graph and we put the links together, and it allowed very fast online speed lookups of information that was very difficult to do with MySQL. So for instance, if you know the 3 Degrees of Kevin Bacon game on IMDb, where you find how closely one actor is related to Kevin Bacon by have they acted in a film with him or with someone else who's acted in a film with him, and so on and so forth. We could run those queries live on our data and display the results on the website, or find the thing like which artist in our database has appeared on stage with the most other artists. The answer, disappointingly, is a compere at a comedy club in London, but it's interesting to find out that he has basically been on stage with every single popular comedian in the UK at some point. Document databases were popular under the NoSQL name a few years ago. The name has faded away because it doesn't really describe what they're good at and what they do. They're not just an alternative to the SQL query language, they are a different concept of storing data. So Martin Kleppmann says that schemaless is a better way to think about these. What they really allow is dynamic fields per row. They don't call them rows, they call them documents. But each document in your database doesn't have to have anything in common with any of the other ones. It can store completely different fields or columns. And it allows nesting, so you can store objects inside objects inside objects. And he says that what this gives you is better impedance match. That means an object in your memory, in your application, can often simply be JSON encoded and stored in a document database without having to go through all the mapping of objects to tables that you might have to do with a relational database. So what you're trying to store in a document database is often exactly what you want to display up to the user on the way out. So use the example of a LinkedIn profile with all the jobs and pictures and references and tags and comments can all be stored inside a single document, meaning rendering the page is very quick, as opposed to the relational format where those would all be stored in many tables and require many queries. So it gives what he calls better locality. One query can retrieve everything that you need to render what you actually want to display to the user. They also allow easy schema evolution, so you can just start, if you want to change the format, you just start storing rows in the new format. You have to make sure that your code can cope with documents in both old and new, or rewrite all the documents to the new format, but there's no formal schema that you have to maintain like there is in MySQL. What document databases are bad at is many-to-many relationships. They almost don't have the concept of relationships. Some of them provide features that let you do it, but really they're intended that you deliberately duplicate or normalize your data in all the documents. Log structured databases are a bit rarer. They're more specialized than the others. They're really good at having data written into them. They're write optimized, it's very, very fast to write. They're not designed to be queried interactively often. They are designed that you just start at the beginning of the log and read the whole log out. And by design, you're storing the same thing multiple times, not in a sort of normalized or denormalized way. Every time the record changes, you just store the changes that have happened to it rather than storing the entire record again. What this makes them really good at is plumbing, connecting different data stores together. Martin Kleppmann in the book talks a lot about using log databases, specifically Kafka, as plumbing and wiring inside a larger data system. So let's write our own database now that we've learned what kinds there are. Here's a simple one adapted from the book. So you can see that the db set function takes a key and a value and appends the string key equals value and then a new line to our database file, which is just a text file. And then to get a value from it, you just need the key. You load the database into memory using the file function, so each line will be a separate entry in the array, and PHP has handled the new lines for us. Then we filter out all those entries, finding ones that start with the key that we're after, and then we just return the first one of those and strip off the key equals string from the beginning. So that's very, very few lines of code, and so it doesn't seem like it would give you a particularly good database. But if we think about it using those terms that we've been talking about, though, the other kinds of database in, what we've got is log structured. It's a key value store. It gives us full history tracking. Every time a value changes, we can see what the old and new values were. It's got excellent write performance. You're just appending to a file. It's very, very easy to back up and restore. There's no special tools required for that. And it has, in general, great compatibility with the entire Unix text processing pipeline. There's almost an uncountable number of tools that you can use to work with this data structure. Some downsides of it, it scales quite poorly. If you have multiple people writing to it, it's not going to handle that very well. And reads in general are very slow. There's no indexes. You have to load the whole file and spool through the whole file every time you're looking for a particular key that you want. Despite these caveats, it's probably better than many of these sort of text-based databases that came with PHP scripts in the early 2000s when I first got into PHP. Lots of those sort of text-based online games had their own hideous storage formats, and replacing those with something like this might have been a genuine improvement, despite its almost impressive simplicity. A concept that Martin Kleppmann brings up is that it's almost never that you're going to want or be able to use just one database. Most applications over a certain size are just going to outgrow what they can do with a single system. So you want to connect multiple databases together to form a data system. You want to use the right tool for the job. You want to separate them into your main storage and your other storage, and you want to connect them together. And he calls this concept polyglot persistence. But I think you can get quite a lot of the advantages of that by doing it yourself, what I call homebrew polyglot persistence, which is where you bung everything in MySQL. So if you need a key value store, you can create a table with a primary key and a blob column. In MySQL, you can use the Memcache plugin, which allows you to use Memcache clients and the protocol to talk directly to an InnoDB table. Cuts out some of the overhead of the SQL language. You can store graph data in a relational database. If you create a vertex table and an edge table, so for instance, your edge table will have the properties and labels that the edge has, and then the primary key of the vertex it goes from, and the primary key of the vertex it goes to. You can query this in SQL, but query is awful. It contains just repeated joins to the same tables again and again and again. In the latest versions of databases, you can use, I think they're called common or recursive table expressions to simplify it. You don't really want to be doing this too much, but we do actually store a graph in the relational database at Eds24. The genres that we apply to events have a graph-like relationship to each other, but we never query it using SQL. We store the genres, the relations between them, and then if we need to do any sort of graph operations on it, we can load the whole dataset into PHP because it's only 50 or so entries. A document database is easy. Again, it's a primary key and then a blob column. In the most up-to-date versions of databases, you can use a JSON column, which then in Postgres or MySQL, they give you functions that allow you to query if your column has particular JSON keys or JSON values. It's not going to be as fast as a full document database, but if you're already running the software, it's extremely useful to be able to get some of that functionality. You can get a full text search database by using full text indexing in MySQL. It's not going to be as good as something dedicated like Elasticsearch, but it'll give you some of the functionality. And a log table is pretty easy to implement as well. You'll do this if you're heavily invested in your primary database technology. It's not worth installing and managing another database system in order to do something simple like our 50 genres in a graph. It's not worth installing Neo4j for that. Or if you need to store a couple of hundred things in a JSON format, the overhead of running extra software is not worth it if you can get most of the functionality inside your primary system. In the book, Martin Kleppmann draws this difference between batch systems and online systems. So batch systems are where you take a set of records from your database, it might be everything in the table, you do some processing on them together. We're probably most familiar with this from cron jobs or overnight jobs that you run on your database. And this is in contrast to an online system, which handles each record as it comes in and as it's updated. You can often write your operations in both formats, but we tend to use batch by default because it's a little easier to understand and to get started with. At Eds24, we run into issues with batch updates because they have a fair bit of lag. If something only happens hourly or overnight, it can be quite a while between someone making a change and that change being visible on the website. So we introduced an update system which When an application makes a change, it writes a little entry into the Beanstalk job queue that we use, and then other systems watch that job queue and make changes to their other data stores based on the change there. And it turns out that this is called the Lambda architecture. It's always nice to find out you've reinvented a wheel. And the Lambda architecture means that you have fast streaming or online updates, and then regular, accurate batch updates. This isn't to say that online updates aren't normally accurate, but you may make a deliberate decision to omit some part of the processing from the online updates. So for instance, we do a lot of recommendations to users, but the methodology behind it is quite intensive, and it would be far too slow to update the recommendations for everybody anytime something changed. So the recommendations are updated only overnight on a batch, because it doesn't matter if they're a day out of date, but other things, images and statuses and prices, are all updated online. I've used this term data system a few times, and he defines it in the book as the difference between an individual piece of software running once at one place within your organization versus all the databases and storage system that you might use throughout. So for instance, at N24 we use MySQL and Memcache and Elasticsearch and Neo4j and then a different MySQL system. And having all these different data storage things together gives you a lot of flexibility and a lot of power, but it can lead to conflicts if you store different things in different places and they have different values. How do you know what's right? And so he talks about the concept of derived data, where primarily you have a system of record, which is your one database that's the source of truth. Data gets written there first. It's the place that if there are any discrepancies anywhere else, you look for the truth, and it's usually normalized to help reduce duplication and make the other jobs easier. You can query it, you can only have a system of record if you want, but it's primarily the source of everything, for the source of the data for the rest of your organization. And then from that you build derived data or secondary stores. So this is where you're going to apply some transformation to the data in your main store to turn it from relational format to a document format, for instance. Derived stores should be rebuildable on demand. So for instance, you lose an Elasticsearch index, it might cause you some operational headaches, some site downtime, but it shouldn't be catastrophic for your organization because you should be able to rebuild it in a reasonable amount of time from your system of record. And data in a derived or secondary store is normally denormalized. You want to have made some changes to it for extra features or performance. A way to help build these secondary stores is what's called change data capture, which I mentioned in the first slide. Change data capture automatically builds little records that tell you what has changed about things in your database by monitoring it. So there are plugins for MySQL and PostgreSQL that watch for update statements and record the changes to the rows. And with change data capture, you then save those into a log database like Apache Kafka. And what this means is a downstream database or secondary store can read that Kafka log from any point in history, maybe starting at point 0, to rebuild entirely from scratch. It will be able to see every change that's happened to everything, and when it catches up to the end, it can keep reading to follow on and keep up with any updates that happen. And what this has done is effectively joined those ideas of batch and online systems together. There's no separate batch rebuild and then online updating. It's all the same process. There's an excellent article about how the New York Times used Apache Kafka to do this kind of stuff. They had multiple different CMSs of different ages and technology backgrounds writing to different databases for media and notes and the articles and the web publishing system. And they put Kafka in as the sort of main data broker between all the other ones. So they would run change data capture on the databases that their CMSs talk to, and all those records would then be stored in Kafka. So things that powered the website or the newspaper printing process could all read from Kafka to make sure everything was up to date. So that's some of the ideas and concepts that I found most useful in the book. And now I'm going to talk about how I went about using them in PHP. So after reading it, I wasn't actually convinced that Kafka was the right tool for us. The warnings about it being hard to run were important because I'm primarily responsible for operations at N24 and I didn't want to take on running another complicated database system. And I want to balance this idea of using the right tool with the job with making the best use of the existing tools that we're already running. So the system I had to build was ingesting data about tickets from various different suppliers, and all of them had different endpoints or ways of getting at the data. All of them had a different understanding or model of what a ticket or an event was, and all of them updated the data on their own timescales. So getting the data from them was the first problem. Some of them gave us APIs that were updated all the time. Some gave us XML files stored on Amazon S3, and some gave us CSV files on an anonymous FTP server. The APIs were updated constantly, the files were updated at random or once a day, and some would be good at telling us that they had changed something, but not what they changed. And so I wanted to write a class that would abstract this away for all the suppliers and effectively give me an interface over them. I point the class at the supplier and it just, however I have to get it, gives me the individual tickets from them. So these are batch operations under the hood. You can only get the data when they update the data, but I wanted to treat it like a stream. And so the way I thought would be good to do this is using generators. So as a refresher on generators, we're basically talking about the yield keyword. And generators are a quick way of creating iterable or iterator things in your application. So you write a function, at some point in there it calls yield with a value, and that will appear to return this generator object to whatever called the function. That calling code is then free to loop over the generator. It will see that X value that was yielded, and then when it loops again, control will go back into the function that called yield, which can do more operations, yield more things. It took me quite a while to get my head around generators. I understand them at this level, but actually trying to solve problems with them, I found this library by Nikita Popov incredibly helpful. He re-implements all the PHP core array functionality using generators. So if there's something you're trying to do and you know there's a PHP function that does what you want, you can go into that library and see how an extremely smart and capable programmer has re-implemented that function using generators. All I really wanted was to be able to go for each supplier as ticket and get all the tickets out, and generators seem like an excellent way to do this. They also helped with dealing with the size of the data. I won't call it big data because it's not in the grand scheme of things. But for instance, one of the suppliers gave us a 2 GB JSON file, which takes well over 16 gigs of RAM to decode, which, I mean, you can always buy more RAM, it's relatively cheap, but seemed excessive given that the rest of the system required only a few hundred megs. And even if you can decode it, it's often fiddly iterating over XML or other formats and extracting what you need. So I found these really excellent libraries. The XML string streamer library there is absolutely brilliant. XML lends itself to being streamed. So what that means is instead of decoding the entire file at once and storing the whole thing in memory, the library will just spool through it and give you down individual parts that you ask for. So in XML, you give it a starting tag and a closing tag that you're after. So I might say event or ticket, and it will just read through it, capturing the little bits that are required and passing them up to me. So in terms of memory usage, it never needs to load the whole file into memory, and all I need to store is just the bit I'm decoding. JSON is a little bit harder. I struggled to find a library that did a good job of this until I came across the magic words pull parser and found this JSON reader library that lets you say the file's going to have a top level object, it's going to have a key, under that key will be an array, inside the array will be objects, and I want you to give me those objects one by one. So let's compare the code that actually handles one of these suppliers with the code that I wanted to have as my interface. So on the left here, we've got the code that actually gets the data from the supplier. So in this case, as an example, I'm using an API that has a simple integer-based paging system. So you can see when you call this function, it loops forever, it makes a request, decodes the body of the request, and then yields out the data. So here I'm using yield from, which you give it an array and it yields each item from the array individually. After that, it increments the page, sees if it needs to continue the loop, and does so. So you can see it will make multiple yield requests for each page, and then eventually the function will complete as normal. On the right hand side, I've got the consuming code. So I call the getFromPageAPI function. It returns this results variable, which at the moment is a generator rather than an array or anything like that. I for each loop over the generator, and for each results as result, each one of those is one of those result objects from inside my function. So you can see that the calling code doesn't need to know about the API. It doesn't need to know that it's batched. It doesn't care about how many pages there are or how many things come out per page. The calling code can just treat it like an infinite stream of events or results. Once I had the raw data from my suppliers, I wanted to normalize it. So in the book, Martin Kleppmann talks about the importance of schemas for backwards and forwards compatibility, being able to know how a particular piece of data was stored at a particular point in time in whichever database it's in. So I was building effectively PHP data transfer objects. So just a simple class with public properties, maybe a few convenience methods for handling dates or adding or subtracting numbers. And they were just JSON serializable. They resembled some of the entities that we have elsewhere in the code base, but I wanted to keep them separate. This had to be effectively a superset of all the data we might have gotten from all the suppliers. So most of them would never fill in every property, but I wanted to capture everything I possibly could from the data they were giving us. So I needed to write code that accepted one of the raw pieces of event data from the code we saw before, and then emit one of these PHP DTO objects. This allows you to write validation code. You can say that one of these objects has to have these particular properties, or these things may be invalid together, and write defined serialization and deserialization code. So I made them JSON serializable, but I put some extra code in to make sure that date times were encoded in the proper ISO format and things like that. Once you've got it normalized, you can then store it. So I decided to use Elasticsearch for storage. It's not a real document database. It doesn't provide some of the functionality, but we were already running it, and it actually provided enough functionality for me to do what I wanted. And a really useful feature that it has is date stamped indexes. So if you've used Elasticsearch, or particularly Logstash or the Elk stack, you might know that Elasticsearch can append the date and time to an index automatically. And then data that arrives on that day or at that time is stored in that one, and you can create a new index for the next day. Elasticsearch will happily query all of these indexes together as if they were one. Logstash uses this to rotate out old data, so you don't need to keep logs for forever, so it makes it very easy to drop them day by day as they become out of date. I wanted this so that each time we import the data from the supplier, I can create a new index with the current date and timestamp on it, and then put all the normalized objects I've created in there. Elasticsearch also has a useful thing called the scroll query, which helps you get all the data back out of an index in a reasonable time frame. But what I really wanted to know about the data was not what it looked like at a particular point in time, although that was useful for data forensics. I wanted to see what they changed. If we do an import on a Monday and an import on a Tuesday, what's really important to the staff in the business is what has that supplier updated or added since the previous day. So in order to do this comparison and find the changes, I looked for a diff tool that worked with Elasticsearch. I found one on GitHub called ESDiff. It had a few bugs in it that I was working on fixing with the author, but whilst I was doing that, I extracted the algorithm out of it and re-implemented it myself in PHP. The advantage of this diff process is it doesn't require holding both the full data sets in memory. That would be prohibitive for some of the larger data sets. It also is quite inefficient. So the real key issue for diffing is not actually comparing individual properties and seeing if they have changed. There's lots of libraries that do that. It's matching the two data sets in the first place to find when they should have the same document. And so this algorithm is really useful because it's generalizable to any data source where you can order them consistently by primary key. So you can write a generator that produces objects for the algorithm that's backed onto Elasticsearch or MySQL. And I've managed to reuse this in a few different places. It's generally a very useful tool to have in your PHP toolbox. And the process is quite simple. You have your two streams or two generators of documents sorted by primary key, and you step over them together. If they give you the document with the same ID, you know you've got the same document, or should be the same one, so you can compare the properties and see what's changed. And to do that, I found a useful library called JSON-diff that works very well with PHP objects. And then if you get a lower or higher ID on one side than the other, then what it means is that one of them has created or deleted a document that was in the other. Otherwise, you would expect it to get all the same ones at the same time. And you advance them on in step until they get back in sync, and then advance them on together. So here's a a diagram of how the matching algorithm works. So you can see we've got our left and our right, which are just our two streams of documents out of Elasticsearch. And then the column of results is what we want to do with it. So we get our first two values from both of them. They both got ID 1, so they are the same document. So we can just diff them to find out the properties that have changed. We advance both the left and the right sides on. We've got ID 2 on both sides, so we can diff them again. We advance them on, both of them on again, and we can see we've now got ID 3 on the left and ID 4 on the right. So because we'd expect to see them in the same order if they were there, what that means is that ID 3 is not present on the right hand side, meaning it must have been deleted. We then advance the left hand side on again, just the left hand side this time, and we've now got ID 4 on both sides. Found the same document, we can diff it. Advance them both on again, and now we've got ID 6 on the left and ID 5 on the right. So again, we would have expected to see ID 5 already if the left side had it, so 5 must be new on the right hand side. So we could omit one of our little change objects saying that the supplier has created ID 5 with these different properties. So I had my source classes that get data from the suppliers, I had my normalization classes, I had some filters and some post-processing, all written as generators. And I wanted to be able to chain them together neatly. By default, they would end up being recursive. Your normalizer would call your source, and your storage would call your normalizer, and your diff would call the storage, and things like that. And it gets quite difficult if you have to nest them all. So I found this very useful class written by a guy called Hugh Grigg. He's got a good blog post explaining how it's built and what it does. And it just is a convenience helper that lets you chain these things on in a sort of fluid API style, rather than having to nest them all together. And then it provides some very useful meta methods like limit and peak, which let you say, I want you to loop over this pipeline that I've created, but stop after 50, or skip the first 50 and then give me 10, which is really useful for debugging when you've got large data sets, you need to find particular parts in it. It supports two kinds of stage in the pipeline. One is a simple function, which takes in a value, does something to it, and returns that value on. They're very easy to write. And the other is a full class, which accepts the generator and then returns a generator. The generator one is really useful because it lets you add and remove things from the pipeline. So whilst you're looping, you can call yield multiple times to produce multiple values from one input, or you can not call yield at all and just skip on to the loop to drop things. So if you want to create filters that remove things from your stream, or create things that turn one input into multiple outputs, you really have to use generators. A big downside of generators for this is you can't type hint them properly. You can type hint that you're going to get the generator object that PHP produces, but because there are no generics in PHP, there's no way of saying that this generator should give me objects of this type, or I need to yield out objects of a particular type. You can obviously use your IDE docblock support to add a comment that suggests that that's what will happen, but there's no language level enforcement of it. And I fell afoul of this quite a few times, especially in the transformation steps of the pipeline, where you're taking in an object of one kind and doing something to it to turn it into a different object. I found it very easy to forget what I was supposed to be getting and producing, and there was no way that PHP could tell me that I'd done it wrong. So I think a lot of the stuff about good data systems engineering boils down to balancing some different properties. So that's using the right tool for the job, the right piece of software that gives you the right functionality and lets you think about your data and your data flow in the most useful way. And then the counterpoint is running less software. That's an idea from Charity Majors, a database admin and an engineer, because it's taking on a lot of debt. It might be that you support it individually, or it's making another team in your organization take on debt. And you also don't want to be the bad workman who blames their tools. You want to maximize the value from the tools that you're getting, run as little software as you can, but still use the right tool for the job. And I think that means building your systems out of composable parts, making use of the features that each database that you currently have provides, but not mixing them all together too much. We used to do this a lot. We would make the database do the work. We would write complicated SQL statements that drew all the tables together and did everything that it possibly could to return a really small amount of finished data to PHP. It's clever, but it makes testing almost impossible. You have to write DB unit tests. There's so much state to maintain, and we just did a very bad job of them. And the system that I built did much better by staying away from the database, using it as storage, making sure that you use it in the right way, as fast and reliable storage, but making your application in PHP do all the actual processing. And this is composing a data system out of parts. If you treat each feature that your database provides as an interface, if you find you outgrow one of them and suddenly you need a real document store or a real full-text search engine, it's much easier to swap out to a dedicated piece of software when you find that you actually need it. In summary then, the Designing Data-Intensive Applications book is well worth reading for any backend engineer or storage engineer, or anyone who's got an interest in the field or any of the concepts I've brought up. It's really well written, it's got great diagrams and pictures, a very easygoing way. Even when it tackles complicated subjects, they're brought in carefully, and all the jargon is defined very well. It's also absolutely packed with references. There are hundreds and hundreds of them if you need to dive or feel you want to dive deeper into any of the topics it brings up. It talks about designating systems of record to help you design and control data flow, which is an idea I found very useful. And then ideas like change data capture and log databases that help you do automatic rebuild of your systems and give you full historical records. Composing data storage out of individual parts from your different databases helps you create things that are reliable, scalable, maintainable, and allows you to swap things out very easily as you grow and change your data. And then when implementing things in PHP, I found that using generators and those streaming parsers helped build applications that handle lots of data easier, and it made them very testable as well. Right, thank you.
Thanks very much, Doug, for that excellent talk. So we have some questions. We've got a question from Dan. For log databases, how do you stop them from growing ever longer?
Yeah, that's a good question. I didn't cover it in the talk. Relating to Kafka in particular, if you imagine you're using it to store all your changes that happen to another database since the beginning of time, and you handle thousands of updates a day, that log is going to grow unmanageable. And in the log database, you can't just chop off the beginning, because if a record was set once at the beginning and is never really updated again, it will just vanish from the record. So Kafka supports an idea called log compaction, where it will step through your records from the beginning and merge them together. If you have lots of updates referring to one particular record, it will build a new entry for later on that says that sets all the values to one part, and then it will reset the beginning of the stream to be that new compacted snapshot. So things that need to import don't need to start from the original beginning; they can start from this snapshot, and then we'll get all the data that's been set up until that point.
Thank you very much. You're getting a lot of love for your background. Yeah, where are you?
I'm in the Planet Express conference room.
Very good. And I suppose on a similar sort of vein, was GDPR a bit of an issue for log databases in terms of if somebody wants their data deleted, how would they go around that?
Yes, I can imagine that would be. Off the top of my head, I haven't used Kafka extensively, so this is a guess. If their data was stored in individual records that only referred to them, you could step through the stream and from the beginning and delete all records. If their data is referenced in other ones, you're effectively going to have to rewrite the whole stream from the beginning to strip out their references and use that compaction process to build a new sort of large insert that is, this is the beginning of time without those bits of information we've been asked to remove. There's probably cleverer ways of handling it, but it does sound like a complicated problem.
Cool, thank you. A couple more questions. Hi Doug, I've been using generators a bit recently, but found it annoying that you can't use ArrayMap, ArrayFilter, and ArrayReduce. Have you found a solution to that? Do you just go back to the for loops? Since I've typed that, you've talked about pipeline classes. Is that what that's for?
The pipeline class doesn't particularly handle those problems. You could add that functionality in, but it's more about composing individual generators. The problem of not being able to use the built-in array functions on generators is quite a long-standing one in PHP. You can't pass iterables or iterators of any kind into the built-in functions, and there's been lots of feature requests on extending and adding that. I don't know how likely they are to pass. It would be a major change or re-implementation of the language. Unfortunately, you do end up re-implementing those functions yourself. So that iter library I mentioned by Nikita Popov contains effectively rewritten versions of those built-in functions that either use generators internally or you can pass generators into to get that functionality. It's a small library It's very fast, and it saves you quite a lot of reinventing the wheel if that's the operations you need to do.
Brilliant, thank you. And another question from Sander King. Is there a downside to composability? Would a monolithic solution be easier to explain?
Xander is my colleague, Ants24, so he's trying to trap me with this one. I don't think so. In a small system, perhaps a monolith would be easier to explain if you can fit all the details on one slide. He says, explain means to document. Again, now, I think either explaining or documenting, if it's built up of composable parts, you can write a high-level explanation about all the different pieces that may be involved or what it's trying to achieve, and then leave the tests or the documentation for individual steps. Keep them separate, so that if you're just trying to find out where your data is flowing to, you don't need to understand all the different parts at once. And then if you find that, oh, it's this particular step, it clearly is responsible, it can be thought of in isolation to all the other parts. You don't need to have an understanding of the rest of the system. You just need to know what comes in and what goes out.
Brilliant. Well, that's the disadvantage of having your colleagues come along and watch your talk. Thanks very much.